calculus, it's important not only to calculate derivatives using formulas, but also to understand what they mean graphically. When you can visualize how a function, its first derivative, and its second derivative relate to one another, you'll find that even advanced problems become much easier to solve. So in this lesson, we'll explore 4 types of graphs and practice sketching their first and second derivatives based on the shapes of the original functions. Graph 1, a cubic function. Let's start with a cubic-shaped curve. We don't need to focus on exact coordinates. What matters here is the overall shape. First, identify the local maximum and local minimum on the original function. Those are the points where the tangent slope is 0, where f prime of x equals 0. Mark those x values on the derivative's x-axis. At the local maximum, the tangent slope changes from positive to negative, so the graph of f prime crosses the x-axis from above to below. At the local minimum, the tangent slope changes from negative to positive, so f prime crosses the x-axis from below to above. Because of the symmetry typical of many cubic functions, the lowest point on f prime usually appears halfway between the maximum and minimum of the original curve. Now let's sketch the second derivative. We look for where the first derivative has extrema. That means where f prime has a local maximum or a local minimum. In this particular case, we can see only one local minimum. Mark that x value on the x-axis of the second derivative graph. At that point, the tangent slope of the first derivative starts to increase, so the second derivative is positive and rising. As a result, the graph of f double prime forms a straight upward slanting line, just like a simple linear function. This matches what we know conceptually. When f double prime of x is positive, the first derivative is increasing and the original function is concave up. When f double prime of x is negative, the first derivative is decreasing and the original function is concave down. When f double prime of x equals 0, the original function has an inflection point where the concavity changes. Graph 2, a single peak curve. Now let's consider a curve that has one smooth peak, a single local maximum. Again, we'll start with the first derivative. At the top of the hill, the tangent slope is 0, so we mark that x value on the derivative's x-axis. For x values greater than 0, the tangent slopes on the original curve are negative, but approach 0 as x goes to infinity. So, the first derivative stays below the axis and approaches 0 from below. For x values less than 0, the tangent slopes are positive, and they also approach 0 as x goes to negative infinity. So f prime will be above the axis on the left, cross the x-axis at the maximum, and then go below the axis on the right dash dash, forming a smooth S-shaped curve. Now let's sketch the second derivative. We find the local maximum and minimum on f prime dash. Those are the points where f double prime equals 0. As f prime approaches both positive and negative infinity, the tangent slopes gradually approach 0. So, the second derivative also approaches 0 toward both ends, forming a gentle wave shape. And the midpoint between the local maximum and minimum of f prime becomes the minimum point of the second derivative. Graph 3. a function with an oblique asymptote. Next, let's look at a function that approaches a slant, or oblique, asymptote. For example, a rational function with a linear asymptote. We can see two critical points, a local maximum and a local minimum. For large positive x, the original function approaches its slant line, so its tangent slope approaches a constant value. That means f prime approaches that constant as x goes to infinity. As x approaches 0 from the right, the tangent slopes drop sharply toward negative infinity dash dash, giving a steep downward curve for f prime. For large negative x, the function again approaches the same slant line, so f prime approaches the same constant value on the left. But as x approaches 0 from the left, the tangent slopes also fall rapidly toward negative infinity. So the first derivative curve rises toward a constant on both ends, but dives down near x equals 0. Now for the second derivative. Since f prime has no local maximum or minimum, f double prime never equals 0. For x greater than 0, the slopes of f prime are all positive, but gradually decrease towards 0. As x approaches 0 from the right, the slopes shoot up toward positive infinity. For x less than 0, the slopes are all negative, approaching 0 as x goes to negative infinity and falling steeply toward negative infinity near x equals 0. Therefore, the second derivative never crosses the x-axis, and the original function has no inflection point. Graph 4. A quartic function. Finally, let's look at a quartic, a fourth-degree curve. Start by identifying the local maxima and minima on the original function and mark those x values on the first derivative's x-axis. Between the first minimum and the maximum, the tangent slope increases from 0, rises to a peak, and then decreases back to 0. The point where this slope stops increasing and starts to decrease is an inflection point on the original function, where the second derivative will be 0. Between the maximum and the next minimum, the slope decreases from 0, becomes negative, and then returns to 0 again. So the graph of f prime takes on a cubic shape. Now, let's draw the second derivative. The process is exactly like what we did earlier for the cubic function. Mark the x values, where the first derivative has a maximum and a minimum. At the maximum, the slope changes from positive to negative, and at the minimum, it changes from negative to positive. So f double prime forms a smooth S-shaped curve, symmetric about the midpoint between those two x values. By practicing how to sketch the first and second derivatives from the shape of the original function, you'll build an intuitive sense for how slope and concavity behave. When you can visualize these relationships mentally, you can solve even the hardest calculus questions. Whether you're preparing for your MCV4U course, the SAT, or AP Calculus.